In this chapter, we will be introducing the concept of integration. In this lesson, we will be looking at how to use partial fractions.
Hi everyone. So in this lesson we're going to take a look at integration by partial fractions. And what we're going to do for the most part in this lesson is I'm just going to show you several examples, and with every one we're just going to kind of build a little bit more into this idea so that you get a pretty good sense of how this particular procedure gets used here. But before we do that, to give you a sense of what's going on here, let me just show you something here. Let's say I've got two rational expressions here. Let's say 2 over x minus 1, and I'm going to add to that 3 over x plus 2. Okay? So I'm going to start with this. We're going to add those together here. So we need to find a common denominator. And so we take a look at that, and I think, well, okay, this particular denominator here is missing the x plus 2 factor, so I'm going to put it in the numerator and the denominator, okay? Because this isn't an equation, this is an expression. So if I'm going to change the rational here, I've got to do it to the numerator and denominator. And then here, same thing, I'm going to multiply this by the missing factor of x minus 1. And so what I will get here is the denominator here will be x minus 1, x plus 2. And then this will be 2, x plus 2, plus 3, x minus 1. I'm going to do this in just a couple of steps here. So x minus 1, x plus 2 is my denominator. And I realize looking back here I switched the order of the two factors down there, but order doesn't matter with multiplication, so it's not a big deal. Now I'm going to distribute 2x plus 4 plus 3x minus 3. And when you add like terms in the numerator, I'm going to get 5x plus 1 over x minus 1, x plus 2. And in fact, I could go one step further and I could expand out that denominator, even though there's really no reason to do it. But I could get, what am I going to get here? X squared plus x minus 2. Okay, so what have I done? Well, nothing that you haven't seen before, really. But now let's take a look at this in a slightly different way here. What if the question was asking me to do this? To find the integral of 5x plus 1 over x squared plus x minus 2 dx. Okay, well now at first glance, what you might think to do here, looking at it, you might think, well, hey, you know what, maybe this is just a substitution problem. So maybe I let u equal, and because I know I'm going to end up taking the derivative of u, maybe I'm going to let it be the term with the higher degree. So maybe I try x squared plus x minus 2. And when I find du by dx, I get 2x plus 1. Now, already looking at that, you should realize that, uh-oh, I'm hoping to get rid of this 5x plus 1, and that isn't going to do it. Because any little alteration that I make to the first term here is going to have to be made to that 1. And so I'm going to run into difficulties here when I try to do my little substitution here. So that's actually not going to work. So how do I do this? Well, you know what? I already know that this expression right here, well, that's equal to that original two fractions that I have, that I started with right here. So what I could do actually is I could take that integral here, just make sure it's on the screen here, the integral of 5x plus 1 over x squared plus x minus 2 dx. I can actually rewrite that as 2 over x minus 1 plus 3 over x plus 2 dx. Now you don't often do that. I mean, at least when you think about your math education up to this point, you don't typically split this up. You typically combine those together into one term. But it turns out in this particular case here, this is actually a far easier thing to work with. Because remember, you're going to split up the integral here. Okay, we're going to make this 2 over x minus 1 dx, and then this is going to add the integral of 3 over x plus 2 dx. And then I can take the integral of both of those separately here. And what I get is 2 multiplied by the natural log, the absolute value of x minus 1, plus 3 times the natural log of the absolute value of x plus 2. And then because this is an indefinite integral, whoops, I have to throw on my arbitrary constant at the end there. So the question becomes, how do I then do that? If I start with this, how do I break it up into this particular, this particular set of rational expressions being added together? Because that is easier to work with. And that is the method of partial fractions that we're going to look at here. So what we'll do here is I'm now going to start to run through some examples. I'll actually start with this one and show you how to break this one up, and then I'll start to show you some other examples that get more and more complicated from here. But that's the idea. We are going to take you from an expression like this, and we're going to split it up into two fractions that are much easier to take the integral of. Okay, so here we go. We're going to take this expression here, 5x plus 1 divided by x squared plus x minus 2. And we're going to split this up. Now, the first thing we got to do, and this is probably no big surprise to anybody, is we got to factor the denominator. And so when we break this up into the two binomials here, x, and we know that the factors of 2 will be 1 and 2. We've got to have a positive there, so positive 2, negative 1. Okay, so now that we know that, okay, and now that we know that this can be broken up, the denominator can be broken up into the product of two linear factors. And in fact, I might even want to write that down here. We've got two linear factors. When we can do that, then what we can do here is write this out as, and actually I'm going to do the x, well, okay, we'll do it like x plus 1 plus 2 here first. So I'll put this as x plus 2 under A plus B x minus 1. So I'm going to assume that I got to here by multiplying these the two denominators together, adding these two numerators together here. Now, when that happens here, what's going to happen is that numerator, 5x plus 1, if I now try to add these two fractions together, what I'm going to end up with is x times x minus 1 plus b times x plus 2. And so we're going to get ax minus a plus bx plus 2b. And when I look at this here and factor out the common x here, what I'll get here is a plus b x and then minus a plus 2b. Okay? Now, it may not look like I've accomplished anything too significant here, but this expression and this expression has to be the same. Or have to be the same, I suppose is how I should have said that. Now, that means that the linear factor here have to be the same. So 5 is going to equal a plus b. And at the same one, my constant here, 1, has got to equal negative a plus 2b. And now I've got a system of equations in two variables. And, well, I can solve that. For example, I can take this and put this underneath here, make this 1 is equal to negative a plus 2b. And I can add those two together. And I'll get 6. A and negative a will cancel. I'll get plus 3b. And then when I divide, I'm going to get that b is equal to 2. And then if b is equal to 2, I can go back up to this initial expression here, and I know automatically that a, okay, a has got to be equal to 3. So now I know, or at least I can write down here, that 5x plus 1 over x squared plus x minus 2, okay, that is going to equal, now I had said at one point here that that was a, and I'll just write this again here, a over x plus 2 plus b over x minus 1. And now I can say that that's equal to 3 over x plus 2 and 2 over x minus 1. And if I go back to my original expression here, that's exactly what I had to start off with. And so that's how you do that. That's the process here of taking this expression here and breaking it back apart into those fractions here that were added, or those rational expressions that were added together. The trick here is how you build it up like this. So if you've got two linear factors here, We assume that those are the two rational expressions. I go through the process of adding or getting the numerators and adding them together, and then compare that to the expression that I'm seeing here. Now, let's take a look at another example, and we're going to alter this just a little bit. All right, now we're going to take a look at an expression here, and we're going to resolve this into two partial fractions here. What we've got here is a linear denominator here, but it shows up twice. Okay, it's squared. So ultimately, we've got a quadratic here. And well, we had a quadratic in the first one, and I've even still got two linear factors here, but it's the same factor twice, okay? So we're squaring that particular factor here. And what you won't do is write this off as a over x plus 2 plus b over x plus 2, because if that was the case, if it started with common factors already, you wouldn't have squared it, right? You wouldn't have multiplied those together. I'd have just added the numerators together. So it can't quite be like that. So what we've got to have here, if we're going to split this up into two different rationals here, then this has got to be x plus 2, and then over here, this has probably got to be x plus 2 squared. And that's actually how we tear this apart here. So I don't know what the numerator is. I don't know what the numerator is. I'm going to figure that out in just a second here. Okay, but now think about what I would do here. In order to add those two fractions together, I'm going to end up multiplying this expression here by x plus 2 in the numerator and denominator, and that's how I'm going to get the x here. I should probably say that, yeah, in all cases here, we're assuming that a and b here are going to be these constants that we're looking for. And so that's how we're going to create that linear function when I multiply numerator and denominator here by x plus 2. So that's what's got to happen here. So I know that 6x plus 7 is going to equal a times x plus 2. But now, because this second rational has that exact same quadratic denominator there, I actually don't need to do anything to it. I'm just going to add b. So it turns out this is actually pretty straightforward. This becomes ax plus 2a plus b. And now to compare this expression to the original one, this here, 6x plus 7, well, this is actually about as straightforward as it gets here. The coefficient of x has got to be the same on both sides here, so that means a has to be equal to 6. And then if a is 6, okay, then I can make this next calculation pretty easily, because I know that 2a plus b has to equal 7, and if I know that a is 6, I can put that in right away. Oops. So that's going to be 12, and when I bring that over, I'm going to get that b is going to equal negative 5. And there we go. So now I've got all the information I need to take 6x plus 7 over x plus 2 squared. I can split that apart now into 6 over x plus 2. And then, I mean, I can do this one of two ways here, but it probably makes more sense to do it like this and write this as adding negative 5 over x plus 2 squared. Okay. And those pieces right there, those pieces are going to be much easier to take the antiderivative of, okay, or the integral of in both cases there. Much easier to work with. So I'm not going to carry on and take the integrals of these expressions here. I just want to show you how you could rip them apart into their corresponding rational terms. Anyway, let's take a look at another one. Okay, actually, before I do another example here, let me just do a quick little aside here, and let's just talk about what would happen in a situation like this. Let's say that we've got a repeated x factor here and a repeated x plus 2 factor. This one comes in 3 times, this one comes in twice here. Let's focus on this factor in the denominator first. What I would do with that one is make this a over x plus b over x squared. Okay? And then I'm going to look at my other factor here. Now, because this is cubic, the best way to go about this is actually break this up into 3 different fractions here, where that's going to be c over x plus 2, d over x plus 2 squared, and e over x plus 2 cubed. Okay, and then I would have to put those all together and then build a system of equations setting it equal to or comparing it to this x cubed minus x plus 2 to get the values of a, b, c, d, and e. Now, that's a little bit beyond in terms of work what we want to do right now. Besides that, I want to show you some other patterns here, but that's what you would do. It's long, but it's not necessarily like hard. I mean, it's hard in the fact that it's long, but other than that, there's nothing overly complicated going on with that. It's just a procedure that you're going to have to kind of work through. Anyway, let me show you a different example. Okay, so in this example, what I want to do is take this negative 2x plus 4 over x squared plus 1 multiplied by x minus 1 squared, and I want to resolve that into partial fractions here. What makes this one different is that now in the denominator, I've got a quadratic factor that I can't split up into linear factors, not without introducing complex numbers here, and I don't want to do that. So I'm kind of stuck here with this. This is about as far as it can go here. And then I've got this repeated linear factor. So how do I do that? Okay, well, we're going to start with this guy right here. So x squared plus 1 could very likely be the denominator of one of my rationals that I put together in here. Because I've got a quadratic down here, what has to happen up here is I've got to have a linear. And that's going to be a general linear ax plus b. If you think back to the other expressions that we've looked at here, okay, when we resolved this, okay, what we did here is we had linear, we had a constant on top. This is basically two linears together. I've got a constant on top here. Now I know that that's a quadratic, but this can be resolved into two linear factors. What we're looking at right here that can't be split up. And so what we've got here is we're going to put a linear expression on top, ax plus b, and then we'll use our expansion here, create a system of equations and solve for a and b. Now at this point here you can probably guess what's coming up. This is going to be x minus 1 under c, and then I'm going to have d over x minus 1 squared, because this is a repeated factor. Okay, now when I get my denominator, I'm going to multiply all those denominators together. So what is that going to look like in the numerator? Well, this is going to get a little bit long here, so just kind of bear with me. To start off with, I know that this is going to equal negative 2x plus 4, I should say. That's my numerator. And now here we go. It's going to be this ax plus b, and that is going to end up multiplied by x minus 1 squared. Okay, now not cubed. I'm not going to multiply this by this. Okay, I don't need to do that. The least common multiple of the denominators is going to be this multiplied by that. I don't need to include this again. But I do need two factors of x minus 1 when I do this. Plus c, and that has got to get multiplied by the x squared plus 1 and an additional factor of x minus 1. And then the d, it's got both of the x minus 1 factors, so all I've got to do with d is multiply that by x squared plus 1. Okay, well that's a little long. It's going to get just a little worse than that. Okay, just a second here. Because what I got to do here is I got to expand out this x minus 1 squared. So this is going to be ax plus b. This will be x squared minus 2x plus 1. This is going to be plus c, and now I can multiply this out. And this is going to be, what is that, x cubed minus x squared plus x minus 1. And then over here I can actually just expand out the d, and that's not a problem. It's going to be dx squared plus d. Okay, now here's where the fun begins. Now I'm going to expand this all out here. So this is going to be ax cubed minus 2ax squared plus ax plus bx squared minus 2bx plus b plus cx cubed minus cx squared plus cx minus c, oh, I'm running out of room here, plus dx squared plus d. And I'm right off the screen there. There we go. Yikes. Now, but all I've done is expanded that all out. Now what I got to do here is I got to collect like terms. Now I've got these two cubic terms, so that's going to make life easy for me. So that's going to be a plus c x cubed. And then for my quadratic term, I've got a few here. I've got this negative 2a, I've got this b, I've got this negative c, and I've even got the d here. So when I put that all together, it's going to be negative 2a plus b minus c plus d x squared. Then for my linear, I've got a negative 2b plus c, and that's it actually. I was looking for more, but that's all I got. So a minus 2b plus c x. And then for my constant, at the end here, I've got the b, negative c, and d. So this is going to be b minus c plus d. Whew. Okay. Now, when you compare that, and I know that's a bit of a beast, but when you compare that to the expression on the left, well, first of all, notice there is no cubic term here. So that means that a plus c has to equal 0. Additionally, there's no quadratic term here. So negative 2a plus b minus c plus d, that's got to equal 0. Now, there is a linear term, negative 2 here. So this a minus 2b plus c has got to equal negative 2. And I do have a constant, 4. So b minus c plus d has got to equal 4. Okay, so that gives us 4 different equations here, and maybe I should just label these. Label them on this side here. So 1, 2, 3, 4. Okay, so what can I do here? Well, actually, take a look at this. Take a good look at this. Notice that in equation 2 and equation 4, I've got b minus c plus d, b minus c plus d. So if I take, let's say, equation 2, and I subtract equation 4, okay, well, negative 2a, there's no a here, so that's going to be negative 2a. But then b minus b goes away, negative c minus negative c goes away, d minus d goes away, and I'm going to have 0 minus 4, so equals negative 4. Well, that's awesome. From there, I'm able to get that a is equal to 2. Okay, well, and then there we go. If I take now equation, what we get here, if we now substitute this into equation 1, okay, a plus c is equal to 0, well then I know that c has got to equal negative 2. Okay, so this is great here. If you now take both of those and plug that into 3, okay, if we take these and plug them into 3 here, I'm going to get, well, I'll just do it like this. I'm going to get 2 minus 2b minus 2 is equal to negative 2 here. Okay, well, the negative 2's will cancel, and I can bring the b over. Anyway, you're going to see really quickly here that that means b is equal to 1. Actually, this is falling into our laps here really, really nicely, because now I know b, c, and a. I can take these and plug these into, for example, into equation 4. Okay, I know that b is 1, so now I can take this information here and the above, substitute those into equation 4. That's a horrible little arrow coming from 2 directions here. But I'm going to get 1 minus negative 2 plus d is equal to 4. So that'll be 3, and when I bring that over, I will get that d, is equal to 1. And there you go. We've got all the pieces we need. So now I know that x cubed minus x plus 2, I'm looking I'm looking at the top of my page. I looked right past the one that I'm actually working on. That wasn't it. For a minute there I was thinking, well, wait a minute, I do have a cubic here. Nope. This was negative 2x plus 4 over x squared plus 1, x minus 1 squared. This is going to equal A is 2, so 2x plus, and then b was 1 over x squared plus 1, plus c was negative 2 over x minus 1, and d was 1 over x minus 1 squared. And again, those pieces, when you work with this, will be much easier to find the integral of. Okay, so this is a good problem here. Now you get to see what you would do with a quadratic factor in the denominator. Okay, I'm going to do one more example with you, and I want you to take a look at this one here and just notice how this one is a little bit different than what we've been doing before. Now, I am working with a quadratic denominator, but it can be split up, or it can be factored into two linear factors here. So I don't need to worry about having the ax plus b in the numerator for any of my fractions here. But the problem that I'm running into is that the degree of the numerator is larger than the degree of the denominator, and we actually haven't done an example where that's the case yet. Okay? In every case that we've worked with, the degree of the denominator was bigger. So what do? Well, the first thing that we're going to do is we're going to divide. So we're going to take x squared minus 1, and we're going to divide that into this 5x cubed minus x squared. Okay? Now, I'm a pretty detail-oriented guy here for the most part, typically. So I'm going to include my linear and my constant terms here. And the reason I do that is because I like things to line up a little bit. When I divide by x squared minus 1, in order for me to get that to look like the largest degree term here, I need to multiply this by 5x. Now, I like to have my linear terms all lined up. Okay, so that's why I do it like that. It just helps me organize it, and it looks pretty to me, if I gotta be honest with you. So 5x multiplied by x squared minus 1 is going to be 5x cubed, okay, now minus 5x. So now when I do the subtraction here, I'm going to get rid of that first term here. The negative x squared is going to drop down, and I get 0 minus negative 5x, so plus 5x, and then there is no constant, but I'll just drop down that 0 there. Basically 0 minus 0 is just 0. And now I start again. What am I going to multiply by x squared so that it looks like this first term? I'm going to multiply by negative 1. So negative x squared, and then this is going to end up being positive 1. And then I do the subtraction. Okay, the x squared terms cancel. 5x minus nothing is just 5x. And 0 minus 1 is going to be negative 1. And that is basically where I stop, because once I've got an expression where the degree of the remainder is less than the divisor, in most cases here I'm done. So now what I've got is I've got that 5x cubed minus x squared over x squared minus 1. That is equivalent to 5x minus 1, there's my quotient, plus 5x minus 1 over x squared minus 1. And now, this is the part that we're going to tear apart into partial fractions. Now, I know that we've already done one very similar to this, but you know what? Let's do it again. Okay, so where was I at here? Well, I'm just going to look at very specifically at the piece that I need to tear apart here. What I've got here is 5x minus 1 over x squared minus 1. So, like we did before, the very first thing that we're going to do is factor, and we are going to get x plus 1, x minus 1. And because I've got two different linear factors, I'm going to assume that this breaks up into a, x plus 1, and b over x minus 1. Okay? Now, when I add those together, I know that we're going to just multiply the denominators together to get that. It's the numerators that I'm concerned about. So I know that 5x minus 1, my numerator, is going to end up being a multiplied by x minus 1 plus b multiplied by x plus 1. Let's expand that out. whoops, that's a terrible looking b. Anyway, when I group together my linear terms, I've got a plus bx, and then I've got plus negative a plus b as my constant. So now I've got the pieces. I know when I compare this to this other numerator, the original numerator, I know that 5, coefficient of x, has to be the same as a plus b, the coefficient of x. I also know that negative 1 has to be the same as negative a plus b. So now I've got these two equations. Once again, I've got this system of equations. I'm going to solve this by elimination. I'm just going to put the negative 1 equals negative a plus b underneath this first one. And I will just add those two expressions together. So 4 is equal to 2b. b is equal to 2. Okay? And if b is equal to 2, because I can go right back up to this expression, I know immediately that a has to be equal to 3. And so now I've done it. I've got all the pieces. So now I can write this out again. I know that 5x cubed, going right back to the original, minus x squared over x squared minus 1 is going to equal, first of all, I had that 5x minus 1. That's the quotient from the division that I did. Now, the remainder I can break up into now my two partial fractions here, and that was going to be a, which is 3, over x plus 1, plus b, which is 2, over x minus 1. Now I've broken that up into pieces that I can now integrate far more easily than what I had worked with before. And in fact, you know what? I tell you what, let's finish this one off at least with the integral here. So let's say now that I was actually integrating this. So 5x cubed minus x squared over x squared minus 1 dx. This would equal the integral of 5x minus 1. Oh, whoops, sorry. I got bracket happy there. I don't know why I did that. Okay. Plus 3 over x plus 1 plus 2 over x minus 1. This is all dx. I would then split this all up into 3 different integrals, plus the integral of 3 over x plus 1 dx, plus the integral of 2 over x minus 1 dx. And I know a lot of you wouldn't need to do that at all. You would basically just jump to the final answer, but I felt somewhat obliged to do that. And so now, taking the antiderivative of this is going to be 5 halves x squared minus x, plus, this is going to end up being 3 multiplied by the natural log of x plus 1, plus 2 multiplied by the natural log, of the absolute value, I should have said before. Absolute value. And in fact, I wrote the absolute value, I just didn't say it, and I didn't do it over there. Plus my arbitrary constant. Whoa, there you go. And that's how you would use partial fractions. I hope that makes sense.